Welcome. We have finally arrived at Euclid. We're going to be spending most of the year reading Euclid, and I really hope that you enjoy him as much as I do. There's a reason we spend so much time with Euclid, and it's because he's great. And so before we really start talking about what we've read in the Elements for this week, we should talk a little bit about who Euclid was, even though most of this stuff I've already mentioned in the introductions for this week. So first, we remember that Euclid's life, we can place it more or less between the death of Plato, which was in 347 BC, and the birth of Archimedes, which was in 287 BC. So based on historical records and whatnot, we are pretty sure that Euclid lived between those two dates. But that's pretty much all we know about that. The other thing that we know about him is that he worked and taught at Alexandria, which was that great Egyptian city of learning, or I should say Greek-Egyptian city of ancient learning. You'll remember that Alexandria is important as well because that's where the great library was, the great library of Alexandria, which was also destroyed in ancient times, which is one of the greatest calamities of history. We'll never know what we lost. Just a tremendous wealth of knowledge was lost at the burning of the library. But that's not doesn't have to do directly with Euclid. So Euclid worked and taught at Alexandria, and he probably received his training in Athens as well, which of course is where Plato was, and probably was trained by the students of Plato, which is a really cool connection. And you also remember that Athens is famous in the ancient world for producing a whole host of very prominent thinkers of the ancient world. Plato is one name I mentioned already. Aristotle is another one who comes from Athens. And there's a whole host of others. And speaking of Athens and this whole host of great minds, there's a painting you ought to be familiar with if you're not already aware of it. It's a painting by Raphael, and it's called The School of Athens. So here is the School of Athens by Raphael. Some of the important people that he includes are Plato and Aristotle, who are here in the center. And he's given us clues, by the way, so that we can tell who's who. They are different ages, but so that's maybe one clue. The elder is going to be obviously Plato because he's older and Aristotle was his pupil. But Aristotle and Plato are also pointing in different directions, which maybe you can see. I'll try to zoom in a little bit to see if that'll help. But you'll notice that Plato is pointing up. Aristotle has his hand extended forward and sort of down. This indicates, of course, Plato's philosophy, which held that the forms of things exist in the realm of the forms, whereas Aristotle believed that the forms are present in the things themselves. Now, I don't have time to get into what exactly that means, but that at least is what their hand motions are signaling, and therefore, because he's pointing upward to the realm of the forms, this is Plato, and because he's saying, no, the forms are here in the things themselves, that's Aristotle. And you can do some research to see who all the rest of these people are. So I'd like to draw your attention to one other figure in this corner. And if you have the Green Lion Press edition, you will recognize this from the cover of the Green Lion Press Euclid. Now, we have a bunch of figures here hunched over a wax tablet. Now, the person drawing is Euclid. This figure here, hunched over with the compass, is Euclid. So if you're wondering where the image for your book came from, well, it comes from this painting. Anyway, so that's pretty neat. Euclid makes an appearance there, along with all of these other important philosophers and thinkers of the ancient world. It's also important for you to know that the Elements, Euclid's Elements, is one of the most influential books of all time. Not only has it profoundly influenced mathematics for millennia, in terms of the rigor and even some of the basic underlying patterns that you see in the elements. And this includes, by the way, certain assumptions that the elements makes, influenced mathematics for centuries. We'll get to see some of that in later years, but we won't really see it this year because we'll just be doing the elements. So that's one way in which the elements has influenced mathematics, but the influence of the elements has extended far beyond the mathematical realm. One of the best examples of this, I think, is with the philosopher Descartes. You might remember Descartes because he's the one who famously said, "I think, therefore I am." Now, the reason Descartes said that is because of Euclid. Now, that's a little bit cryptic. I'll explain what I mean. Descartes was also a mathematician as well as a philosopher, and you might have come across the Cartesian coordinate system, or the Cartesian coordinate plane. It's called Cartesian because of Descartes. Also, if you ever have done some algebra or pre-algebra and you've had to find x, the reason we search for x rather than other variables, other letters for variables, is because of Descartes. He was the first one to use x as a variable and it sort of stuck. Or I should say he was the first one to use x consistently as a variable and it stuck. But anyway, so Descartes was a mathematician as well as a philosopher, and he was really in love with Euclid. He thought that the certainty that Euclid brought to mathematics by beginning with a few indisputable axioms and definitions, as we've seen this week, and then out of them constructing an entire system of geometry where every step along the way was very carefully analyzed and was completely certain. He loved that idea so much that he wondered, why can't we do the same thing with philosophy, right? All kinds of philosophers have all kinds of different ideas, and it's hard for people to agree on philosophy, but it's easy for people to agree on mathematics. What if we take Euclid's approach to the approach that he presents in the Elements and apply that to philosophy? What would happen? Would we suddenly have a more certain philosophy? Descartes certainly thought so. So what he tried to do was he tried to take the same process that Euclid presents in the Elements and apply it to philosophy. And the way that he did this was he thought, okay, we need to begin just like Euclid does with a set of indisputable axioms, right? In Euclid, the axioms are the postulates and the common notions. So he thought, in philosophy, what would that be? What would we begin with? They have to be things which are self-evident and indisputably true, right? That's because they're self-evident. So he thought, well, what if we start with this idea? He said, what do you think? Well, no, because that's not really self-evident because I can doubt it, right? If it's doubtable, it's not self-evident. So he kept doubting all these things, and finally he got to the point where he said, well, how do I even know that I exist, right? Can I doubt my own existence? So he doubted whether, so just to back up a little bit, he began by doubting, of course, his senses. He thought, well, the senses don't always tell us true information about the world, or at least we're prone to misinterpret it, right? Have you ever touched something cold and thought it was hot for a split second, or vice versa? If you have, you know just how tricky the senses can be, right? Or because of optical illusions, we think that we see something, but we really don't see what we think that we see. And so he was quick to doubt his senses and to say, well, those are not always completely accurate ways of gaining truth, and so we can doubt the veracity of the senses. And we can even doubt them to the point where we assume, or where we can wonder whether or not anything that we think that we know with our senses is actually true, right? This is sort of a common theme in science fiction and whatnot. where people are, operating within a simulated reality, like a computer simulation or something, and they think that they're in the real world, but really everything that they're sensing is an illusion. So Descartes thought, okay, well, how do I know that I'm not dreaming, right? Which would be his version of something like a simulated reality. How do I know that I'm not dreaming? And he thought, well, I don't know that. So even though I think that this table is really here, right? I can touch it, I can feel it. I can't really prove to myself that I'm not imagining this table. So he thought, well, I can doubt my senses then. So let's just throw that out. Let's just pretend like I can't know that this table is here. What else can I not assume? What else needs to be proven? So then he thought, well, God's existence, well, I can imagine a world without God, so I'm going to doubt God's existence as well. So I'm doubting my senses, doubting God's existence. Then he thought, well, what about my own existence? How do I know that I exist? And he tried to doubt his own existence. It didn't work, because he realized, wait a minute, if I doubt my own existence, well, doesn't that mean that there has to be something doing the doubting? If there isn't anything to do the doubting, how can the doubting happen? So, well, obviously the answer is, well, it can't, right? If there's nothing to do the doubting, there cannot be a doubter, right? So he thought, wait a minute, because I'm doubting my own existence, that means that there's a doubter, me, and because I know that I'm doubting, because I'm doing it, therefore I must exist, right? The very fact that I can doubt my own existence proves that I do in fact exist. And that's where he said, I think, therefore I am. Because he realized that he was doubting. Somebody had to be doing that doubting. It was him. Ta-da! He really does exist. And from that point, so he took that point as his starting point, as his fundamental axiom. And so he began with that idea and tried, just like Euclid does, to begin with a set of axioms to construct a system of geometry. Descartes tried to do the same thing with philosophy, taking this one idea that because he could doubt his own existence, he existed, and he attempted from that point to construct a coherent philosophy. And so what he did was he thought, well, okay, so if I exist, I know that I'm a contingent being, which means that he doesn't exist. He's not self-existent. In other words, his existence depends upon something else. Because he thought, well, if my existence didn't depend on anything else, I would be God, but I know that I'm not God. Right? Because a minute ago he was doubting whether or not he even existed, so obviously he's not God. So he thought, okay, I'm not God, and so I know that my existence depends upon something else. That thing that my existence depends on has to be God. So he was able then to reason from his own existence back to God's existence. So he thought, okay, so I exist, God exists, can I trust my senses? And then he thought, well, if God exists, he would have to be a good God. And see, he had reasons for that, by the way, which I'm not going to get into, but he reasoned that if God exists, he had to be a good God. And that a good God would not lie or would not create people who were unable to know truth. And so he reasoned then that because God exists and because God is good, therefore God is the kind of being who would make creatures who would be able to know what is true. That means, Descartes thought, that my senses have to be fairly accurate indicators of reality, right? And so when I touch this table really is here because God is good and he wouldn't give me senses that never told me anything true. And so I can assume with a great deal of certainty that this table is a real table, that I'm really sitting here, that this is not an illusion. And then from those ideas, Descartes went on further to develop his philosophy. But I hope that you can see, at least to some degree, the similarity between Descartes' method and Euclid's method. Descartes even called his method a geometric method. He tried to apply the geometric method to philosophy. So that's just one example of Euclid's tremendous influence. Okay, so let's examine the questions for definition 1. The first question is, do points exist? In what sense do they exist or not? Well, of course, points exist. The real question is, in what sense do they exist? For instance, if I draw a point, there's a point, we have to immediately say that that's not really a point. This is a representation of a point, but it isn't a point, because a point you wouldn't be able to see, because the definition of a point is that it has no part. This obviously has a part. It doesn't matter how small we try to make the point. I'll make a very small one. You may not even be able to see it, but I just drew a very, very small point right there. But that's not really a point either, because it has a particular size. I can even zoom in, zoom in, zoom in, zoom in. And you see, if we zoom in far enough, the point, what was a point, now displays as a couple pixels, which together look like a rectangle. So the point, then, is that points do not exist physically. Any physical representation of a point is not really a point. I'm not going to discuss the other questions here. I just wanted to make that one point clear before we go on to definition 2, which is what I would like to do now. The question here for definition 2 is, most modern definitions call a line a two-dimensional figure that forms the shortest distance between 2 points, which we can draw like this, for instance, and continues infinitely in both directions. How does Euclid's definition differ? Well, if we define a line as the shortest distance between 2 points, the one point would be at this side, one point would be at this side. And again, remember, we realize this is not really a line. This is a representation of a line, but it's not really a line. If this were really a line, we wouldn't be able to see it, because Euclid defines a line as a breadthless length, which means it wouldn't have any width, so we wouldn't be able to see it. But we are able to see this one, so it's not actually a line. Now, if we consider the modern definition, which is a line is the shortest distance between 2 points, one thing that we notice is that if we take the shortest distance between 2 points, that line's going to be straight, right? It's going to be a straight line. Euclid does not confuse any of these concepts. He tackles lines first in terms of their dimensionality, to say that they have length but no breadth, and then he goes on later to define straight lines separately from that. Even if we adjust the modern definition to say that a straight line is the shortest distance between 2 points, it doesn't really solve the problem that Euclid is addressing, because what Euclid is doing is he is discussing these figures, these concepts, in terms of their dimensionality, starting from something with no dimension, 0 dimensions, which is a point, and moving up to lines, which are one-dimensional figures, and then later on moving to plane surfaces, which are, of course, 2-dimensional figures, and so on. So he has a very clear progression, which would be more difficult to observe in something like the modern definition. There's a reason Euclid does this the way that he does. Definition 3, what is an extremity? Well, extremity is simply the limit of something, right? So if we have a line again, the extremity would just be where it stops, where the line actually stops. That's the extremity. And if we zoom in, of course, we recognize this isn't really a line because it has width. But the extremity is just where the line actually stops. That's it. Definition 4, most modern textbook definitions assume lines to be straight. Why does Euclid add this definition of straight lines? Why is definition 3 insufficient by itself? So what you should have in your journals is something like what I've already said, that Euclid is very careful in addressing one concept at a time. He doesn't combine several concepts into a definition. He addresses them separately. So first he talks about lines in terms of their dimensionality, and then later he addresses the concept of straightness, which is a separate
concept. And Euclid is very careful to do this, because when you mix concepts together in a definition, in one sense, it can be more difficult to make sure that the definition isn't assuming too much. But if you only have one idea in a definition, it makes it much clearer. Definition 5, why doesn't Euclid define a surface as being flat? So I'm going to use this as my surface. We're going to pretend that this rectangle is a surface. Or maybe I can draw it in perspective. We'll do that. So I'll draw it like it's going to be in perspective here, like a tabletop. There we go. There's our surface. Now, why doesn't Euclid define a surface as being flat? Now, the one that I've drawn is flat, but he doesn't define it as being flat for the same reason that he doesn't define lines as being straight. He defines straightness separately from the figure itself, and he does the same thing here. So it doesn't surprise us then that when he defines a flat surface, he defines it in terms of straight lines. That should make sense. So the second question here is, what earlier definitions does definition 5 resemble or parallel? Well, if we look at definition 5, which says a surface is that which has length and breadth only, it should remind us of definitions 2, a line is a breadthless length, and definition 1, a point is that which has no part, because these are the ones which deal with the figure's dimensionality. So definition 5 falls into that category as well. Definition 6. What earlier definitions does definition 6 resemble or parallel? Definition 6 is the extremities of a surface are lines. So again, we're dealing with extremities. And if we look at the figure that I've drawn here, we can clearly see that the extremities are lines, right? Because I drew lines to represent my surface. So because it's dealing with extremities, of course, it parallels definition 3, which is the extremities of a line are points, right? So a line ends in points, but a surface ends in lines. Definition 7. What earlier definitions does definition 7 resemble or parallel? Definition 7 says a plane surface is a surface which lies evenly with the straight lines on itself, and that really is the flat surface I mentioned a moment ago. So this one, of course, parallels, well, the definition for straight lines. In fact, it even appeals to it in some way. So that's going to parallel definition 4. So moving on now to epicycle C, let's take a look at some of the other questions. I'm not going to go through all of them because I think that some of these are fairly self-explanatory, or at least the answers should not have been too difficult to guess at. I do want us to pause, however, on definitions 9 and 15. So definition 9, my question here asks, why is it important to distinguish between rectilineal angles and non-rectilineal angles? So a rectilineal angle, is just an angle formed by two straight lines, your typical idea of an angle. So if we have, on the other hand, curved lines, which maybe will look something like this. So if we have curves like so, the point at where they meet, we can't measure that angle in quite the same way. This angle we can measure because the lines are straight, and the angle is the same measurement at any place we measure it. Here, however, if we measure here, that's one angle measurement. If we measure here in the same way, we get a different measurement. And so the angles can't be measured in quite the same way as rectilineal angles. So for that reason, of course, he has to distinguish rectilineal angles separately. He mentions them separately, defines them separately, just to make sure that it's clear what kind of angles are in view. Definition 15 is about circles. So if I draw something like a circle, that's fairly circular. We have to ask, what does it mean that the circle is the figure contained by the line? So the question is the line the part of the circle? Now, this thing that I've drawn is not really a line. I mean, we call it a line, but geometrically, this is not a line, because a geometric line has zero width, and this obviously has a width so that you can see it. So in this figure, then, we'd have to say that the circle is contained by the line, which means that the circle isn't really part of the line, but the circle is everything inside the line. Now, in the ideal sense, in the geometric sense, this isn't really hard to imagine because the line doesn't have any width anyway. So because the line doesn't have any width, then the line can't be part of the circle because it doesn't have any width that would take up any area in the circle. So I hope that that makes sense. But in this case, because we do have a line that does have a width, the best we can say is the circle is everything inside the line. So it's on the inside edge. It doesn't touch the edge. It isn't the edge. It's just everything inside the edge of this circle is the circle. The line isn't the circle. Everything inside is the circle, based on the definitions that we've already had. Now we come to epicycle D, and we'll look at some of these questions as well. So definition 18, my question here says, why is the center of a semicircle the same as that of a circle? And what you should have written in your journals is something to the effect of a semicircle's center being defined in the same way as a circle's center. A circle's center is defined as that point where any line falling from the circumference to the center is all going to be the same length, right? So this is an implicit definition of radius as well, which is important to keep in mind because we're going to be using radii, but we're not actually going to have a formal definition of the radius. So just understand that the radius, the definition of a radius, is implied in definition 15. Those are those equal straight lines falling from the center. And because we define a semicircle in the same way, right, just sort of cut the circle in half, we define it in the same way as the circle, and so the radii of a semicircle are all going to be the same too, right? Those are all going to be the same, and for that reason, the center of the semicircle is the same as that of the circle. So now we come to the postulates and common notions. So a postulate is something which is begged for, and a common notion is something which is, well, a common notion. It's something which should be self-evident. So we have 5 postulates and 5 common notions. And if you look at the common notions, these are things which everyone recognizes to be true. They are immediately obvious. Those are the common notions. The postulates are not so much things which are immediately obvious, but rather things that Euclid is asking, almost like he's asking our permission for, because he's essentially begging us to grant him these things. And these are abilities that he requests. The first one is to draw a straight line from any point to any point. So if I have a point here and a point here, he says, well, we have to assume that we can draw a straight line from those points, because unless we can do that, geometry is going to be awfully difficult. Next, he says to produce a finite straight line continuously in a straight line. So that means if we have a straight line already, like so, this means that we should be able to continue it. We have to have the ability to continue that straight line in a straight line, like this. So we have to be able to pick up where we left off and continue the line. That's another ability that we have to assume. Then he says to describe a circle with any center and distance. So we have to at least agree that theoretically speaking, we can draw any circle with any center, any distance, any size radius, any size circle has to at least be theoretically possible for us to draw. And then he says here, this isn't an ability so much as just an assumption, but he says we have to assume as well that all right angles are equal to one another. Now this is something which you might be puzzled by because it may seem too obvious. But see, here's the thing. How do we know that a right angle in the northern hemisphere is the same as a right angle in the southern hemisphere? Or how do we know that a right angle in Missouri is going to be the same as a right angle in South Africa? Well, we can't really prove it. We just have to assume that these are going to be equal. And maybe to explain the problem a little bit further, you wouldn't be able to just pick up a right angle and then take it to some other part of the world and compare it with that right angle. Because how do you know that the right angle didn't change on the journey? Maybe it changed an infinitesimal amount. You have no way of proving that. So all we can do is assume that every right angle is equal to every other right angle. That's something which we have to assume because we can't prove it. Now, of course, we all have to agree that's a pretty reasonable assumption. There's nothing unreasonable about assuming that right angles are all equal. We can't prove it. That's something we have to essentially take on faith, but I think it's a very reasonable position. So now we come to postulate 5, which I have already remarked some on in the introduction to epicycle D, but I'll say more about now. So The problem with postulate 5, as I've already said, is that it's so different from the other postulates. If we read them, we see this immediately. The first one's very simple. We've already discussed the first 4. But the first one's very simple, to draw a straight line from any point to any point. That's very, very simple. To produce a finite straight line continuously in a straight line, again, very simple. To describe a circle with any center and distance, that all right angles are equal to one another. These are all so simple they can be expressed in just a few words, and each one's only a line long. Then we get to postulate 5, which suddenly is huge. This is much larger than the other postulates, and that creates a problem for us because it doesn't look like the kind of thing which is self-evident or which should be considered self-evident. In fact, if you compare postulate 5 to some of the enunciations for the propositions that we're going to see next week, you'll find that proposition 5 looks more like the enunciation to a proposition. That is to say, it looks more like a theorem, the claim of a theorem, than it does a postulate. So to put that another way, postulate 5 looks like the kind of thing that needs to be proven rather than assumed. So let's analyze for a moment what it is that this postulate is saying. It says that if a straight line falling on 2 straight lines, we have 3 lines altogether. Let's go ahead and draw those. We have one straight line like so, and then our second straight line, which I'm going to draw at an angle like this. If a straight line falling on 2 straight lines, so these are the 2 straight lines there, and then we're going to have a straight line falling upon them, which I'll draw something like that. So 2 straight lines, a line falling upon the straight lines, and he says if it makes the interior angles on the same side less than 2 right angles, which is to say that if the angles here, so if this angle plus this angle, when they're added up together, are equal to less than 2 right angles, then the 2 straight lines, if produced indefinitely, that is to say produced this way and this way, they will eventually meet some point over here on that side on which are the angles less than the 2 right angles. So to put it another way, if we have 2 angles, I should say if we have 3 lines like so, and these angles here on the same side, the interior angles are less than 2 right angles, we form a triangle. Even if it's a very, very long and skinny triangle, eventually, because these 2 lines are going to meet at some point over here, we get a triangle. Now, this claim may seem fairly obvious. However, it's only obvious if we have exaggerated cases like this one, where you can actually see the lines heading toward each other. But let me ask you this question as a hypothetical, right? What if we have 2 lines, but they are so close to being parallel that you would have to extend them out, not for what might be a few inches in this case, but for miles, maybe even light years. So imagine these 2 lines stretching out into space for light years. And in this case, what if the reason they stretch out into space for light years before actually meeting is because the angles here, the interior angles, are just barely less than 2 right angles. In other words, what if the difference is so small that the triangle which we theoretically create ends up being extremely long, not just a mile long, but light years in size? Well, and then what if we take it one step further? What if we make a triangle that's even larger, which means that the lines get even closer to being parallel, right? And so it's even longer and the lines still continue to meet. Well, we can keep this thought exercise going for a while, and it starts to get a little bit mind-boggling, right? And because of these infinitesimally small cases, or the cases where the angles are less than 2 right angles by such a small amount, we have to ask ourselves, is this always true? Or are there some cases where they would be so small, or I should say that the difference from the 2 right angles is so small that the lines seem to be parallel. So all that to say that this is a really large claim, and it's something that we cannot merely assume because of the nature of the claim. This is something that actually needs to be proven. We have to be able to prove this beyond a shadow of a doubt. We can't simply assume that if we keep making the angles larger but still keep them less than 2 right angles, that they will always meet. How do we know that there isn't some point along that spectrum where the angles suddenly or where the lines suddenly become parallel, but the angles are still less than 2 right angles? How do we know that that's not the case? This has to be proven, cannot merely be assumed. Now, as it turns out, geometers have been trying to prove the fifth postulate for centuries. For many, many centuries, no one has ever succeeded in proving the fifth postulate. That doesn't mean that it's false, by the way, just because nobody can prove it. I mean, you can't really prove any of these other ones either, but nobody's questioning them. But this one, because of the nature of the claim, we feel that it needs to be proven, but nobody's been able to do it. So, several geometers, one of them, maybe the more prominent name among them is Lobachevsky, who was a Russian, realized, well, what happens then if the fifth postulate is just assumed to be false? That is to say, what if we just cross it out altogether? Can we still do geometry? And what happens when we try to do geometry? Well, what happens is if you throw out the fifth postulate because it's too sketchy, you end up producing what is known as non-Euclidean geometry, because Euclid's geometry depends upon the fifth postulate to work. But in non-Euclidean geometry, you get really bizarre cases like this, where you have a line and you have 2 lines that approach each other infinitely but never meet. And so you can have 2 lines that are infinitely approaching each other. And by the way, straight lines. 2 straight lines that approach each other infinitely but never meet, and so they're considered parallel, even though if we were to measure the distance between the lines here and measure the distance between the lines here, it would be 2 different distances. But yet the lines would never meet at any point over here. That seems really strange, and in fact it seems impossible, but what we have to say is that the logic makes it necessary to accept it. And this is something which makes non-Euclidean geometry really challenging, is that it violates all of our conceptions of the way that geometry works. Another thing that happens in non-Euclidean geometry as well is you get triangles which you have to draw a certain way. The triangles end up having to be drawn something like this, and the reason is that the angles in the triangle add up to less than 2 right angles. You may know, and if you don't, you'll discover this year, but the angles in a triangle are equal to 2 right angles. That's if you add up all the angles in a triangle, they're equal to 2 right angles. But in non-Euclidean geometry, you can have a triangle where the angles are less than 2 right angles. So we'd have to say this is a triangle and all the lines are straight, which I had to draw them bent to make the angles the right size so that they're equal to less than 2 right angles, but I have to define these lines that look bent and call them straight lines. It gets very, very trippy. This is the reason why I said that non-Euclidean geometry seems psychedelic. It's because when you are doing non-Euclidean geometry, you really kind of feel like you're on drugs because things which ordinarily make sense do not make sense, and things which should not make sense make sense. So it's very, very strange. And the strangest thing of all is that non-Euclidean geometry is not just a kind of mathematical or intellectual fiction. It really works, and it has real and practical applications. But all that to say that the fifth postulate has caused a lot of controversy, and for that reason, it should also teach us that we have to be very, very careful as mathematicians, because if we assume something which needs to be proven, later on we may discover that that assumption has limited us in some way, and we also need to be careful in analyzing the things that we encounter to make sure that they are really justified. Now, the fifth postulate is true, and it can also be negated,
and still provide a legitimate geometry. To give you one example how this might work, the reason that Euclidean geometry makes sense to us is because we experience the world as a flat world, right? We experience the world as flat, but we know that the world is actually a globe. And so over short distances, Euclidean geometry makes sense. But what if you're trying to chart the routes of airplanes making intercontinental or cross-continental journeys? And so here we have planes flying, let's say, from the Americas to Europe. So that's a pretty far distance, and you can't treat it like the planes are flying in a straight line because they're actually flying across a globe, which is curved. And so at any given point, we experience it as a straight line, but the line is actually bent. And if you draw a triangle on a globe, you'll find that in one sense, it's not really a regular triangle. It's actually more like a Lobachevskian or a non-Euclidean triangle. And if you draw a triangle on the inside of a globe, on the other side, if you can imagine yourself inside the globe rather than on the outside, you would get a triangle where the angles add up to less than 2 right angles. Just like if you draw it on the outside, you would have a case where the triangle has more than 2 right angles, or I should say the angles add up to more than 2 right angles. So maybe that provides you with an idea of how Euclidean geometry and Lobachevskian geometry are both valid geometries with real-world applications, although they seem, at least on paper, to contradict each other. Both can actually exist happily in the same universe. So that's all I'm going to get into today. So for next time, go ahead and work through cycle 6, and we'll review all those propositions and exercises next week.